All right, I think we can start. Let me say hello, everyone. Welcome to another talk in our webinar series. Today we have Michael Blanton from the University of New York talking about near and far galaxies observed with the Sloan Digital Sky Survey. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA MCTI. Michael, thank you very much for being with us today. The floor is yours.
Hey, thanks. It's a pleasure to be here. Although one of the pleasures of giving seminars in this way is I get to be outside while I do it. So you'll have to excuse the birds tweeting in the background. So I'm here to talk about the Sloan Digital Sky Survey and what it's told us in recent years about galaxies and cosmology. This is work that in fact LIneA has contributed. I'm very happy to present it here. And I will give a little bit of a warning that the work that Sloan has done, it covers a lot of ground. And so I am both going to be a little bit rapid when I talk about the science results, and also incomplete. So my talk, I will pre-warn you, has both of those flaws. But first, I'm going to start the talk just by telling you a bit about how SDSS works, how it functions, or at least how it's functioned up until now. And then I'll talk about the phase I've been involved in recently as director, which is just coming to a close, SDSS-IV. And I will tell you about its components and what it's been up to over the last 6 or 7 years. And then I will very briefly at the end talk about what's next for SDSS, which has in fact already begun. So again, for context, this work is work that comes out of a very large collaboration, 70 different institutions, more than 1,000, I think probably close to 2,000 at this point, active scientists all across the world, including this part of the world. And it's funded, the Sloan Digital Sky Survey is funded in large part by the Sloan Foundation, in a little part by the Department of Energy, but primarily by institutions like yours. Here's just a picture of a small segment of the collaboration in a collaboration meeting recently, or not that recently, a few years ago, obviously. If you want to understand our funding model, it's easy to remember, because if you're familiar with this famous chart showing how much dark energy there is in the universe, how much dark matter there is in the universe versus atoms, meaning sort of ordinary matter, and the fractions of these that we see today, then the funding model for SDSS-IV has been just like this, with the DOE providing the support equivalent to the baryons. The Sloan Foundation is the dark matter, and the member institutions are in fact the dark energy, providing the bulk of our funding. So what do we do? Well, we map the sky in various ways, and we use two 2.5 meter telescopes to do this. One at Apache Point Observatory in New Mexico, and one at Las Campanas Observatory in Chile. And 2.5 meter telescopes are not incredibly big. The special thing about these telescopes is that they have a wide field of view. So at APO, you can cover a diameter of 3 degrees on the sky, or 6 times the size of the full moon, and about 2/3 of that at the telescope at Las Campanas. And in this focal plane that covers this wide patch of sky, we have a high level of what we call multiplexing, meaning that we can take spectra simultaneously of many objects. So for example, in optical spectra, we can take when we were operating in SDSS-IV, we could take 1,000 spectra at a time, or 300 infrared spectra at a time, or 17 integral field spectroscopy units at a time. And then for each of those observations, we could do 8 or 9 of them per night. And so you can really rapidly accumulate the sky, spectra over a wide area of sky. And so here's an example of one of the spectroscopic plates, and you sort of zoom in here, you see all these holes. Into these holes are plugged these optical fibers, which brings the light back to the spectrographs for each of these individual objects represented by one of these little circles. So these plates into which these fibers are put, these holes have to be drilled very precisely, as you can see there, and a very well calibrated machine, which you can see here. And this, what's going on here is that it's drilling the holes in these plates, you know, either 300 of them or 1,000 of them, or however many we need for that particular plate. All this fluid here is just keeping the plate at a uniform temperature. And we go and we measure each plate carefully. And the requirement here is that these holes have to be in the right place to about 10 microns from point to point across the plate. So they have to be drilled very, very exactly because we need to place the fibers very precisely on the objects that we want to. So after these plates are drilled and measured, they get sent to the observatories. So here's one of them here, and this is our telescope. This is a very old picture of the SDSS telescope at Apache Point right over here, out on this pier. And at Las Campanas, we use the DuPont telescope, which was built quite a long time ago in the 70s. And it sits out at the end of the ridge here. And it's a very similar telescope, actually, although the dome is and the infrastructure around it is very different. Once it gets there, every day, the plates have to be plugged with these optical fibers. You see somebody doing that here in this time-lapse video. And so you prepare 8 or 9 of these during the day. And then during the night, you put each of these plates in turn onto the pre-prepared plates onto the telescope with a quick changeover of about 20 minutes in between them. And so that's how the operation sort of works. And at the end, what you have is you have a bunch of spectra. There's a very similar system that we built in 2017. So this, sorry, let me back up. This system here that's being depicted here, this is at Apache Point, and this has been operating this way since about 1999. Since about 2017, early 2017, we've been doing the same thing at Las Campanas, that second telescope I showed you. And there's a team that's that was managed by 7 Chilean or 8 Chilean institutions that actually operated this system. And we had a whole plate and fiber plugging system we built there, and a new spectrograph that we built for that purpose. Here are 2 of the observers busy preparing to plug a plate. And so this was a new system in SDSS-IV. In fact, this is one of the major contributions LIneA made. They actually managed the on-mountain server support, which is extremely important to keeping this system running efficiently. So the system, as I said, it's very efficient at getting lots of spectra. To actually sort of visualize that, if you look at, for example, the eBOSS component of SDSS-IV, which is the optical spectroscopy, it did 1,000 fibers at a time. And for each fiber, you get a spectrum like one of these panels here. So there's 20 spectra depicted here, various different objects. You can see a quasar, a distant galaxy. There must be a star here somewhere. But you get all the different sorts of objects. But if to visualize 1,000 of those, it looks something like this this particular plate. And so it's really a lot of spectra just from one plate. And there's 3 or 4 million of these over the lifetime of SDSS. These plates, which are these sort of 1/8 inch thick, aluminum things, most of them over the history of SDSS were sold for scrap for $5 a plate. Aluminum, you can sell it. But in 2014, we sort of had the realization that people were really interested in these objects because they were like, associated with a part of the sky, and each hole was associated with a galaxy or a star, of which we had data. And so they're really interesting artifacts of our research and are actually really good educational tools. So starting in 2014, we started distributing these to local schools through our partner universities, along with a curriculum associated with them. And so, and we still have thousands of these plates. And so you can imagine, filling basically every astronomy classroom, I don't know, maybe in the world, with with one of these plates, which is, with its own patch of sky associated with it. So there are other clever things that people have done with these plates over the years. They've made artwork, they've made tables, they've made portals in their doorway. And this is one I like. This is an artist who's the wife of one of the engineers who used to work on the telescope and infrastructure. And she made a replica of the Sloan telescope out of plates. This was an installation in Seattle a number of years ago. So there's all sorts of clever things people do with these artifacts. They're one of the more fun aspects of the survey. So great, we have this system, and this system can acquire spectra of objects over large patches of sky very rapidly. So what are we doing with it? So I'm going to talk about what we did with it in the Sloan Digital Sky Survey 4, this particular phase of SDSS. And what we did with it were 3 things that I'll talk about in turn. One of which was eBOSS, which was a cosmological survey, so a very large redshift survey, making a 3-dimensional map of the universe. Another was a totally separate survey using infrared spectra to map our own galaxy. And this is really where the work in the Southern Hemisphere becomes so important, because that allows us to see the center of our galaxy, the Magellanic Clouds, and really fill out all the different parts of our galaxy. And then the third, so this is the very distant in eBOSS, the relatively close in APOGEE 2, and then in the middle we have MaNGA, which is doing integral field spectroscopy, resolved spectroscopy of 10,000 nearby galaxies. And so I'll talk about each of these in that order: eBOSS, then APOGEE, and then MaNGA. And all of these were done in a 6-year-ish program. It started on July 1st, 2014. It was meant to end a little bit earlier than it did, but we got a little bit hung up in the middle of 2020 because of the ongoing global pandemic. So we actually completed on the morning of January 21st of this year. So eBOSS actually ended even earlier. eBOSS ended a couple of years ago. And this was really the culmination of 20 years of work doing redshift surveys from the SDSS system. And the really neat thing I find about this is, if you look back, SDSS has been around for a while. It was planned starting in the early 90s. And if you look at the first plans for the survey and you ask, well, what volume did they really want to do? This is a picture of the volume that they wanted to do. And to scale, this is the volume, and the redshifts out to which eBOSS has actually done. So we've done a much larger effective volume, in the technical sense that cosmologists mean that word, a much larger effective volume, and actually gone to much earlier epochs in the universe. And all of this data is now publicly available. This work of mapping the universe has effectively ended at the Sloan telescope as of the end of eBOSS, and it's really the dark energy spectroscopic instrument, the DESI project, who's picking this up now from the MAIAL at Kitt Peak. That's a different project, but a lot of the eBOSS team has migrated to the DESI project, including some of you in the audience, I see. But this is, for the moment, eBOSS is the state of the art in this area. And I'll only really be able to talk about the most, the highest level things that eBOSS did. And really the headline thing is measuring what's called the Baryon Acoustic Oscillation. And the Baryon Acoustic Oscillation is a feature that arises in the early universe because when, in the early universe, the universe is this hot gas, and some parts of the gas are a little denser and higher pressure than others. And those higher pressure regions sort of drive an acoustic wave outward, and around every little, high pressure spot, there'll be a little shell around it of, an expanding shell that's driven by, the fact that there was originally this hot spot. That shell continues to grow until, as long as you have this hot gas. But at the epoch of the cosmic microwave background, the electrons and the photons, basically the baryons and the photons, decouple, and this shell stops expanding and it's sort of frozen in place. And we're lucky because at the same time, for sort of the same reasons, the universe becomes transparent. And so we can see the pattern of fluctuations, which include, in a statistical sense, all these little overlapping shells from all the little denser spots in the universe. And we can see it as the cosmic microwave background. And we can look, in this case, this is kind of something that's the spherical harmonic transform. It's something like the Fourier transform of these fluctuations on the sky. And these fluctuations are closely related to the size of the shell that was created. And in fact, from these observations, you can infer in megaparsecs, or any units you want, the size of that shell that's been created. In the low universe, in the low redshift universe nearby, if we map the universe and we look at the correlation function of galaxies, we see the remnants of that shell. So the correlation function is telling you, if I'm sitting on a galaxy and I look further and further away from me, I will, I can measure how likely it is for me to find another galaxy. So it's shown here. And nearby, I'm likely to find another galaxy because galaxies pull towards each other gravitationally. So if I'm in a galaxy, there's likely to be one nearby me. So that's what this bright spot is telling you. And then that declines as you go further out to larger distances. And it'll decline until you get, just a probability that's just the random probability of finding an object. But in between, we see the remnants of this shell that's imposed by the fact that there was this early acoustic wave. And the signature in the low redshift universe is this shell. And in fact, we can, because we're measuring a redshift, we actually are measuring something a little bit different when we look transverse to the direction we're looking versus line of sight. And so this shell actually isn't necessarily, gives us two pieces of information, basically. It tells us something about the universe along the line of sight and something about it transverse. And so what it really, in fact, tells you is because the CMB gives you a distance, and you're measuring, because you're measuring redshifts, you're measuring a difference of velocities. I have a distance, and I have a difference of velocities, and then I can divide them, and I get a velocity per unit distance. And that, in fact, is the same units as the Hubble constant, which is, the speed with which something is moving away from us, divided by the distance that it's away. And so what we actually measure when we measure along the line of sight is we measure the Hubble parameter at whatever redshift this map has been made. And then transverse to the line of sight, it's something more like what you would think of as the distance to the sample we're looking at. And we can do this all in eBOSS at 1 to 2% precision. So we get these two different measurements of distance as a function of redshift, one of which is something like the expansion rate, and one of which is something like a distance. And in fact, and here we're, it's being shown in this rather funny units just to make the plot, just to make the plot a little more readable. But these data points here are all data points that come out of SDSS, including eBOSS. And the lines are the simplest model of the expansion history of the universe. How the universe expands tells us how it was expanding at each moment, and it tells us what distance everything, will be as a function of its redshift, its speed away from us, its redshift. And the simplest model, which is shown as these lines and seems to go through the points pretty well, just has some dark matter and baryons making up the matter density, where 80% of this has to, or 85% of this has to be dark matter. But then it also requires an acceleration of the expansion, which is actually somewhat related to the curvature of this line here, the green one. And then it also requires just a normalization, which is just the expansion rate today, h0, the Hubble constant. So the simplest model just involves these two basic components plus basically, when are you looking at the universe, h0. And that explains things actually pretty well. And you can ask the question, well, what if I expanded that model? What if I made that model more complicated? Instead of a cosmological constant, which is the sort of the simplest thing to make the universe accelerate, which it has to do, I could make that cosmological constant have a different, be dark energy with some different equation of state. Cosmological constant would have -1 for this W0 value. And then you can make that W0, you can make it change with time, with some time dependence, which is quantified by this WA. And you could also, instead of having a flat universe, which is what this model is, you could make the universe curved. You could have some space-time curvature. And that's quantified by this omega k. And what you find when you take the eBOSS results and SDSS results, and you combine it with the cosmic microwave background results, and you combine it with the supernovae results, which also measure the distance as a function of redshift, you get these gray bands here. And what you find is that the normal model, a flat universe with a cosmological constant, so this value is -1, and it doesn't change with time, so WA is 0. That explains everything that we see. So that's really interesting. This cosmological constant model is not itself a obviously natural thing to happen. And so it's very interesting that we're seeing no deviation from this simple model, and it's becoming very interesting, and I think will become even more interesting in the epoch of DESI, that these curvature constraints are getting so small. So there's another, so the most basic model of the universe has survived. And it continues to support this idea that there's some cosmological constant causing the universe to accelerate. In addition, there's a there's another thing you get out of these measurements. As I said, you're measuring a distance. You know, the CMB measures a distance, and we measure a velocity that should correspond to that distance. And so we're actually getting like a Hubble constant measurement. And so the models that we have predict what the Hubble constant should be measured as locally. And if you do that, under this simple model, just a flat lambda CDM model, just a cosmological constant, you get that there's a particular value that this constant should have. It should be about a little less than 68 with some small error bars. The outer error bars here are 95% error bars, 2 sigma error bars. And, you know, under this simplest model, it can't really vary very much away from that. If all you had was the CMB trying to predict what this H0 was at low redshift, if all you had was the cosmic microwave background, then once I expanded my model to include, you know, a strange equation of a state, or an open model, or a time varying model, once you do that, then the CMB doesn't constrain this H0 parameter at all. There's no constraint on it. However, you can let all of those things be free. And if you include the large scale structure measurements from SDSS, you find there's still pretty tight constraints on what this local expansion can be. And then, but of course, people have worked for decades to measure the local expansion. And if you look at, say, the Cepheid distance ladder based measurements, for in this case from shoes, you find that they get a much higher value, and they're relatively precise as well. This is their 95% confidence interval. And these things exclude each other by quite a bit. So this is like something like a 5 sigma difference, which is very, very significant. And so this remains as something of a puzzle. Something could be different about physics early in the universe, or something could be wrong with these measurements. There's other measurements which support this very high H0 value. On the other hand, they're also similar precision measurements that that find a somewhat lower value. This is from the Carnegie project, which is based on a slightly different version of the distance ladder that's not very much in conflict with the large scale structure measurements. And so this is still something to be argued over. And I will not argue over it today. My main point is that this problem can only really be shown to be a problem with the Hubble constant specifically, rather than these other possible variations of the standard model with the help of the large scale structure data. You cannot do it with CMB alone. That's my main point. Okay, so that's sort of a very brief summary of the most high level things done with eBOSS. But SDSS-IV and its successors are really now turning to focus on the lower redshift universe. And and first I'm going to talk about the very low redshift universe, which is to say our own galaxy. And so APOGEE 2 is a project which also takes many, many spectra across the sky. But in this case, instead of taking optical spectra, it's taking infrared spectra, in this case meaning about 1.5 or 1.6 microns. And the idea of infrared spectra is that 1.5, 1.6 microns is substantially bigger than the typical interstellar dust particle. And so that means that this light is much less affected by the dust in our galaxy. And that allows us to do really the first comprehensive spectroscopic survey of the galaxy that actually can probe the disk of our galaxy to large distances from us. And so this sort of egg splatter here shown in the pink is an estimate of our rough coverage of the galaxy. Where here, the spiral arms are shown in this cartoon. There's the bulge. And this just shows, just for a particular tip of the red giant branch star, how far APOGEE can actually see within the disk. So in the most extincted parts of the disk. And so this is very nice because we can see much more distant than, say, the competing optical surveys. And what we can do with those observations is we can measure the velocities of stars very precisely, but we can also measure element abundances. So each spectrum looks like one of these lines here. This is shown from just a set of stars from high metallicity at the bottom to low metallicity at the top. And it's just showing all the various features you can measure in these snippets of the spectrum. And from these, you can measure elemental abundances precisely for about 15 or 20 abundances. And of course, you can measure the stellar parameters as well. So here are a bunch of the abundances that you can measure: vanadium, titanium, calcium, and also carbon, nitrogen, oxygen. Anyway, I won't read them all out. You can measure these and their trends very, very precisely. And I'll talk a little bit about some of the stuff we've learned from these patterns. So what do we want to know from these sorts of observations? Well, really what we want to know is, we want to untangle the history of the Milky Way. How did its bar form? What's the chemistry and star formation history of its disk? How is its disk structured? What are its dynamics? And then also, because we can also look in the halo of our galaxy, what's the structure of the halo? What's its accretion history? And APOGEE has been able to address all of these questions. And I'll only be able to talk about a small slice of what it's addressed. So I want to first talk about what I consider the biggest surprise to come out of the APOGEE observations, which was the ability to measure the ages of individual stars. And so I think there are likely people in the audience who are much more expert than me about this, but APOGEE targets mostly red giant branch stars. And red giant branch stars experience something called dredge up, where carbon and nitrogen that have been formed earlier in its history get dredged up. And the nature of the dredge up tends to depend on the mass of the star. And higher mass stars get more nitrogen dredged up than carbon. And that means that if we look at the nitrogen to carbon ratio, we can determine the mass of the star. And if we know the mass of the star and we know other things about the star, for example, the fact that it's on the red giant branch, we can determine its age. And at fixed metallicity and other things, an older star will have a higher carbon to nitrogen ratio because an older star will be lower mass. This method of measuring an age has been calibrated against astroseismology. That was the work of Martig, and it's been applied to a huge sample of APOGEE spectra. And this capability was really developed by on the basis of Martig's work by Ness, Melissa Ness. And so what you can see is a pattern like this one. So here I'm just plotting This is the alpha abundances, things like oxygen, magnesium, as a divided by iron, where the sun would be at 0 here, and this is some logarithmic scale. And on the x-axis is how much iron there is, where again 0 is the sun. So the sun would live here on this plot. And this is a sort of where stars tend to live on a plot like this. And here it's colored by the age of the star, where I can't see the thing, but red must be older and blue must be younger, as all sensible plots like this will have. And so the reason for that, actually this Martig paper is very interesting because they're particularly interested in young stars that are living up here. But the reason you get this general pattern where the older stars are at high alpha and the lower stars are at low alpha, or sometimes called solar abundances, is because that's what happens to stars when they're enriched early in the process of a star formation, history. Early enrichment is going to be dominated by the stars that blow up earliest, which is the core collapse supernovae, the most massive stars. And those have yields which are rich in these alpha elements and not as rich in these iron elements. So when you have the products of early enrichment in your star, thus you're probably an older star, you have high alpha. And low alpha reflects, the generations after that of type 1a supernovae and stellar wind, or type 1a supernovae and stellar winds and things like that, that build up iron relative to alpha. And so those tend to have solar abundances, which are more of a mixture of these two nucleosynthetic processes. So this pattern here that you see, sort of naturally arises. And for APOGEE, I'm going to be talking about both the ages, but I'll also talk a little bit about these alpha and iron patterns. So a really straightforward thing that comes out of this, once you have these ages, is you can see directly the inside out growth of the Milky Way. So we live here in the Milky Way. That's its center. Here in the NESS paper, you see sort of the average age of stars as a function of their position in the galaxy. This is height from the disk in the Z direction here. But if you just look in the disk and you just follow this outwards, you see that in the disk, the stars are old here, and then they get younger, which means that the star formation in the inner parts of the disk happened earlier than in the outer parts of the disk. Not a particularly surprising result, but one that is really amazing to see directly in the ages of the field stars. And this McGrath paper is just another nice demonstration of this, showing the surface density profile in the disk as a function of age, where you really see that the younger profiles in blue here are constant, have more density out, at solar radii than the older populations. And there's lots of good work on here. I'd recommend this Frankel paper as well. So actually, I'm going to skip this story because it's a little bit involved, but and go straight to this. And with the ages, and you can look at the disk in a little more detail because we have ages and we have dynamics because we have a radial velocity. And because many of these stars are in Gaia, we actually have three-dimensional velocities. So you can actually look as a function of age at various radii within the galaxy at the relationship between the vertical velocity dispersion, how hot the population is in the vertical direction of the disk, versus the age. And you see the age metallicity, the age velocity relation, which we've known for decades in the local part of the galaxy. You can see it both in the local part of the galaxy, which is sort of these greenish points, but also further out in the galaxy in the red, and in the inner parts of the galaxy. And you can map it and its properties as a function of position in the galaxy. And you can also separate the high alpha and low alpha sequences and study them as separate populations. So there's a whole literature about what all of this means, and how to connect this to simulations of galaxies. But the contribution I think that this program has made is to give us a very, very detailed look at the structure, both in, both the radial structure and the age structure and the velocity structure of this system. And one of the key things you'll notice is that as the population gets older, of course, it gets hotter, both in the vertical and, as it sort of has to, in the radial direction. And the other, what I would say is the second really surprising thing to me that came out of APOGEE is really nailing down the consequences of the fact that you have a radial velocity dispersion of these stars that develops, because the radial velocity dispersion increases, but in addition to that, you get really large radial excursions of stars. So this is something that simulations actually predict in dynamic disks. This is a simulation from a few years ago where it's just showing a few individual stars and showing their histories. And you can see that some of, ones that start here, here's one that ends up, it starts 5.5 kiloparsecs away from the center of the galaxy. It ends up at close to solar radii. And other stars, sort of vary quite a bit. Other stars stay where they are. And these processes are mostly due to scattering off these, transient spiral arms of the galaxy. And a consequence, and what happened, and so this is something called radial migration. And you can see the signatures of radial migration in these age, radius and age patterns of stars. So, for example, there's various ways you can look at this, but here's one that's looking sort of a little bit further out from, just taking a section of the Milky Way a little bit further out than the sun. But you can look at this at a number of different radii and see the same effect. And what's being shown here is the age of stars and their metallicities. And so if you look at age versus metallicity, if the stars are just going along and staying at nearly the same radii and the gas is doing the same, then what should happen is that early on you have low metallicity stars forming, they enrich the gas, you get higher metallicity stars forming, and as the age of the stars gets younger, that is, as time goes on, you get more metal-enriched stars. And so when we look at our population, we expect the oldest stars to be metal poor and the youngest stars to be metal rich. And that's what you see up to about solar metallicity in this part of the galaxy, which is about the metallicity of the gas. And so that's great. But then at intermediate ages, there's this population of high metallicity stars. And so what's up with those stars? And the natural explanation is that these are stars that were formed at high metallicity in more inner parts of the galaxy where the metallicity is high, got to those metallicities earlier, and then were scattered out into this region of the galaxy, scattered out to 10 kiloparsecs. And so this V, or I don't know quite what it is, this shape, a sideways V, is a signature of, interpreted as a signature of this radial migration. And you can see this in other patterns as well. For example, if you look at the resulting metallicity distribution, what you expect as a function of distance is, sorry, as a function of radius, is you expect you expect without radial migration, you expect the same pattern at each radius. Just you've reached a different metallicity. And in fact, you expect this skewness that you see in this case in the blue towards lower metallicity. But what you in fact see is you see that as you get to lower metallicity parts of the galaxy, the skewness actually goes the other way. And actually, you get this very symmetric distribution known as the G-dwarf problem locally in the galaxy. And this pattern is something that this paper by Loebman showed arose from simulations of our galaxy very naturally from this process of radial migration. And so inner parts of the galaxy, the higher metallicity parts, have this skewness to low metallicity, and then that skewness reverses as you go to higher radius. And the interpretation from these simulations indicates that about half of the stars in our neighborhood would have migrated from inner parts of the galaxy, of order half. So this is a very interesting discovery, which I think really came out of APOGEE. So let me skip that. So this whole story of how our galaxy formed is massively complex. I've only concentrated on a couple of different aspects of it, its age structure and this radial migration. But there's many more aspects that APOGEE is looking at that I really can't do justice to. And the key to making this progress is really being able to see through the dust with the infrared observations. So I'm going to end, and whenever I get this talk, MaNGA gets a little bit of short shrift, but that's okay. Because I put it at the end. MaNGA is the last piece of SDSS-IV I'm going to talk about. And you can put this in context by thinking, well, APOGEE is looking at a galaxy like this, but there are all these other types of galaxies here shown in the illustrious simulations. What about all of those? Like, don't we want to compare, all of the different, the whole diversity of different galaxy types to what we see in the universe? And so MaNGA's aim is to look, we can't look in quite the detail you can look in APOGEE, but it's to look at these galaxies in more detail than we've been able to do so before for a large sample. So MaNGA has aimed to look at 10,000 galaxies like this by doing spatially resolved, in this case, 1 to 2 kiloparsec resolution observations. So you have a fiber, at a bunch of different locations across the galaxy. Take an optical spectra, shown on the bottom here, at each of those locations. And then you can see the emission lines, the continuum from the stars. You can measure the dynamics, and you learn all these things about the internal structure of this galaxy. We aim to do 10,000 unique galaxies, but the last official count has 10,010. I've heard rumors recently that actually 10 of these might have accidentally been repeats. So we might have hit exactly 10,000. I'm not quite sure yet, but at any rate, it's very, very close to 10,000. And so you can do a whole bunch of different things with this sort of data. So for one of the interesting things you can do is you can dynamically characterize the galaxies. So for example, if you look at galaxies like our own, they're rotating. They have big rotating disks, and we can measure those rotating disks. We refer to those as a fast rotator. We can see this side's going away from us, this side's coming towards us. This is just measuring the Doppler shift of the emission lines. Or actually, this is the Doppler shift in this case I think of the stellar light. And you can look at the velocity dispersion of the stellar light, and you see it's strongest in the center. There's a bulge in the center, which is a big velocity dispersion. But there are some galaxies which are slow rotators, where they're just, the stars have random orbits, so there's no net rotation. And those ones are supported primarily by the velocity dispersion of the system, which is uniform roughly throughout the system. And so you can classify galaxies, and this is just the particular classification, by the amount by which they're supported by rotation versus the velocity dispersion. And this lambda parameter that you can calculate or measure from the galaxies is shown on the y-axis. And the x-axis is just the ellipticity of the galaxy. And what's shown here, the bottom, these red points, are basically where elliptical galaxies lie. They're slow rotators. And they can be oblate or prolate or spherical, but they're generally slowly rotating. Whereas the spiral galaxies and S0 galaxies tend to live up here. And so this becomes a classifier that allows you to distinguish dynamically different galaxies. And you can ask questions like, well, if I'm interested in how elliptical galaxies form and I want a good way of identifying them, I can identify them as slow rotators. And I can ask, well, do I really find these things in group environments more often than I find them in underdense environments if I pick out a certain mass of galaxies? If I pick out, high mass galaxies, for example, like, a narrow range, as shown here in the red, and I ask, are there really more slow rotating galaxies at this mass in denser regions? The answer, in fact, is yes. That it appears from our data that in the denser regions, you get more slow rotators. This is a really interesting result because if you ask that question of different ways of finding early type galaxies like red, if you identify them as red or not star forming, you would actually find a much weaker dependence once you took out the dependence on mass. But by looking directly at the dynamics, you get a different answer. And so this is telling us something about the way the environment of galaxies, affects how they end up forming and their properties. So you can take this further. You can deconstruct galaxies into different components, into their bulge and disk, and then quantify their dynamical properties. So you can make, for example, a plot of the bulges and disks of spiral galaxies in this same space. And you find the disks, not surprisingly, tend to be like rotating. And the bulges tend to not be rotating, but there's a population of non-rotating bulges. And in fact, a lot of these bulges tend to be much more extended, much higher inclination in some sense than elliptical galaxies. You can go even further with the dynamics. You can take a single galaxy and the single location in the galaxy, and you can decompose the individual stellar populations into old and young. And so you can look at, in fact, the difference relative to the gas rotation, the difference in the rotation speed of the old stars and the young stars. And since the whole galaxy has to be supported, the old stars and the young stars both have to be in equilibrium. If the stars are moving more slowly than the gas, that means they must have a higher velocity dispersion. So that's something that comes out of stellar dynamics. And so what this tells you is, in many cases, these old stars are moving much more slowly than the young stars. And so they have a higher velocity dispersion. And so what you're seeing here is the same effect that we saw in APOGEE. You're seeing the age-velocity relationship of stars here in distant galaxies, where you're separating the old stars and the young stars purely spectroscopically. And you're seeing that the old stars have a higher velocity dispersion. And what you find, since you can look at more than one galaxy, is you find a big variety of whether these populations tend to be very, nearly the same, or whether they tend to be very different. And so what we've learned is that the age-velocity relation that APOGEE is measuring is not universal to galaxies. It varies among galaxies, which must be another clue about where it comes from. And then the final thing I'll talk about, because I really have to wrap up, is that you can also in MaNGA talk about the inside-out growth of galaxies that we saw in APOGEE. So, you can take these spectra and you can look at their stellar populations and basically time slice the galaxies as a function of position in the galaxy. And you can measure, for example, the time by which 95% of the stars had to have formed as a function of the radius. And so what you see is that, this is separated by different galaxy masses, but you see for the higher mass galaxies, the inner parts did tend to form earlier than the outer parts in terms of the stars, but that is a function of mass. So we see again where the Milky Way lives in the scope of all galaxies. It lives somewhere in the middle here. And so one of the really interesting trends in SDSS lately has been doing these similar sorts of analyses in APOGEE and MaNGA to see where the Milky Way fits into this larger universe of galaxies. So there's really so much more that I couldn't talk about. I just skipped over a bunch of it there. And there's even more that didn't even make it to my slides, which I'm just gonna list here. And I guess you can go back and pause this list if you wanna look at it. But there's a huge amount of data, a huge amount of science that's come out of it. So SDSS-IV has ended its observations. What comes after? SDSS-V. All I will say is two things. One is that we're moving away from plates and we're actually moving to a fiber robot system, which has all sorts of really interesting new things you can do with it. And so there's new capabilities coming online this year, hopefully. And two, if you want to know more about that, invite one or more of these four people, Juna Kohlmeyer, Jennifer Johnson, Scott Anderson, or Neve Drury, to talk about what SDSS-V is going to do. So I'm just going to leave up the summary and say, we've had a successful 6-ish year mission. We've mapped we've made what's still the largest 3-dimensional map of the universe. We've looked at all the components of the Milky Way. We've dissected a huge sample of nearby galaxies. We need help untangling all of this information and all of this data. And many of you have access to it already, and I encourage you to look at it. And if you don't, if you're at an institution that doesn't, it's all going to be public by the end of 2021. And I invite you to take a look at it. So I think I went slightly long, but now I'm done. Thank you.
It was worth it. Thank you, Michael.
Thank you very much, Michael, for this remarkable talk. We have, do you have 10 or so minutes for questions?
I have time, yes.
Okay, thank you. So we have now a little time for questions. If you joined us on YouTube, you can put your questions in the comments section and I will redirect it to Michael. If you're with us in Zoom, you can ask it yourself. There is a reaction button if you want. It helps if you use the reaction, if you use the raise hand option. So questions? Okay, we have a question from YouTube from Pedro Henrique César. He says, thank you very much for this nice presentation. What will be the next steps of MaNGA? You have improvements and ideas to continue with the survey?
For MaNGA, that's a very interesting case because we spent a lot of time thinking about, well, should we use this MaNGA hardware like for a MaNGA 2? And the MaNGA team, the conclusion was, you know what, if you really wanted, the conclusion was that getting 20,000 galaxies instead of 10,000 galaxies wouldn't necessarily teach you much more. If you wanted to look at more distant galaxies or look at high resolution, the MUSE spectrograph is so amazing, and there'll be thousands of galaxies from MUSE in the next few years. Maybe that's the right way to go. What the MaNGA team really wanted to do was look at some of like the more fundamental questions about how you understand this, this sort of integral field spectroscopy, how you untangle, the gas emission and the stellar emission and really understand it. And so what they decided to do, most of the people on that team, is do this local volume mapper project, which is actually incredibly innovative. What they're doing is they're actually building a bunch more DESI spectrographs. They just took the DESI spectrograph design, because DESI, like that team, basically perfected the design of a moderate resolution optical spectrograph. It's just like the spectrograph to build if you want to do that. And so local volume mapper is just going to build a few more of those, and it's going to put them on like 30 centimeter size telescopes. So very small telescopes. But that gives you, at the at F5, at that F ratio, that gives you a very wide field of view. And so what they're going to do is they're going to do big maps of the Milky Way with these small telescopes. And you'll see the stars and the gas at high space, physical resolution. And so what they really want to do is understand, what they mean by local volume is like the Milky Way or M31 or the LMC. Right? Things like this to really understand the physics at 10 parsecs and 100 parsecs. So much smaller scale than a kiloparsec. And so that's where SDSS-V is going, which is a really interesting direction. Sorry, that was a long answer to your question. I'm really just making up for the fact that I didn't leave enough time for this last slide.
Well, thanks, Michael. More questions? We still have some time. I have more, I'd like to ask more an advice than a question, if I may. What would you say for early career scientists? Where to look? What needs to be done?
Well, sir, so I'll speak to the field of galaxy evolution a little bit, and leaving aside cosmology, which would be a somewhat different answer, because galaxy evolution is sort of splitting, in a lot of ways, is splitting into, looking at look-back studies of the high redshift universe. So like things like the prime focus spectrograph, JWST, things where you're really probing redshifts 2 and above. And there's a whole community and a whole approach of look-back studies, which is like indispensable. And then there's a more archaeological approach. And I think one of the things that's really interesting lately is this connection that I was alluding to between, like, how do I use archaeological observations of nearby galaxies? Like, how do I really extract a star formation history, right? How do I get that? How do I know that I'm getting it right? That's a really difficult question, but it feels like a question that in the next few years, we're actually going to be able to answer in a more sophisticated and certain way than we were 10 years ago or at the start of my career. And I think it's things like looking at local stellar populations, looking in detail at the gas around us, looking, getting better stellar libraries. I feel like there's a lot of astrophysics which spans sort of like the Milky Way to nearby galaxy world and incorporates like a lot of the radio observations that are becoming possible now. That I think there's a lot of work to do on the underpinnings of our understanding of like galaxy star formation histories, things which we have the statistics to understand with MaNGA, but nobody really believes nobody really believes the error bars we get because of the systematic uncertainties. And to me, that feels like the most interesting piece of it. Because also, if you understand that stuff, there's sort of a longer time scale set of questions about what's going on in galaxies, which connects to like, well, what is dark matter really doing inside of galaxies? Can we learn stuff about dark matter by the structure of galaxies and their history, which feels like we're maybe another generation away from being able to do that really well. But I think the direction is really understanding this small scale fundamental stuff better. Anyway, that's for whatever it's worth.
Yeah, that's
Come back
good
in
advice.
20 years and see if I'm right.
Yeah, that's. Thank you very much. I think we have time for a last quick question. Let's see if we have. Okay, if there are no more questions, we will now wrap this up. Let me say some last words. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Francesco Valentino from the University of Copenhagen talking about the life and death of massive galaxies. Thank you everyone for attending, and a special thanks for Michael. Thank you for having the time for us.
Yeah, it was great. Thank you so much.
Okay, it was a remarkable talk. Thank you very much. Everyone, have a great day. Stay safe. Have a great weekend, and I hope to see you all next week. Bye-bye. Thanks, Michael.
Thanks.
That's great. Thank you.
I'm having the usual problem of finding my Zoom window to log out.
Oh, thank you.
But take care down there. It was great to meet you.